Добрый день. Меня зовут Сергей Федоров, и сегодня я с удовольствием представляю вам доклад моей коллеги Te-Yuan, которая будет рассказывать о том, как устроен стриминг в Netflix, будет рассказывать про основные компоненты и различные оптимизации, которые она и ее команда сделала. Te-Yuan абсолютно замечательный человек и замечательный специалист. Она выпускница Стэнфорда. И она автор очень большого количества алгоритмов оптимизации в сфере видеостриминга, включая первую реализацию адаптивного алгоритма на основе мониторинга буфера. Сегодня она руководит командой, которая продолжает оптимизировать адаптивный стриминг в Netflix, и сегодня она будет про это рассказывать. Доклад будет по-английски, потому что, в отличие от меня, Te-Yuan не выросла в России и по-русски не говорит, поэтому я сейчас переключусь, и мы потихоньку перейдем к докладу. До этого момента я упомяну, что у нас есть чат в Zoom, где вы можете задавать вопросы по-русски или по-английски, если что, я помогу перевести. Часть вопросов я постараюсь задать в ходе основной сессии, потом мы сможем переключиться в дискуссию после, где мы тоже сможем обсудить какие-то моменты. Hello, Te-Yuan. Good morning. Thanks a lot for joining us. I really appreciate you joining the conference and sharing your knowledge. How are you doing this morning?
Very good. And to play Veche to everyone, thank you for having me here today.
Te-Yuan, I think your Russian is getting much better. Hopefully, maybe in a year, I'll do some progress and we'll make you to do a longer introduction. Well, yeah.
Please do.
But yeah, I think with that opening, I will transfer that. Sorry, I think we still have a few more minutes maybe to chat a little bit before we start the main presentation. So I'm curious, Te-Yuan, what's on your mind today in terms of doing optimizations? Like what's for this week? What are you most interested or concerned about when it comes to work, or maybe not work?
Yeah. So when it comes to work, there are so many things we can learn. So this week, actually, what's in my mind is to understand the value of higher video quality, and trying to understand how consumer value the video quality. And there are many different ways that we can get more understanding. One way I will talk about, which is the A/B testing. But there are also other ways, such as consumer insight, where we invite customer into the office and then conduct interview between the Netflix researchers and the customers. So there are kind of two complementary ways to each other. And because one is like the A/B testing is the macro view, versus the consumer insight, we really zoom into like individual preferences and understand from a very micro perspective to learn how they perceive playback experience in terms of video quality and many other things as well. Yeah, and because my background is actually computer science, right? So I actually didn't have a lot of experience conducting this kind of consumer interview. Those actually require more of a psychology background to understand the human emotion and the human perception of different level of qualities. And so that's something I really want to learn. And here at Netflix, I'm privileged to have that opportunity to see both the macro side of things as well as the micro side of things.
Yeah, and Te-Yuan, I think this is so powerful because even besides Netflix, I think all of us have been in a very large scale consumer science experiment for the last 2 years as it comes to transitioning into having the video-based interactions front and center of our life. So I think it's I'm looking forward to the more learnings that your team and your partners would come up with. All right, I think we can slowly transition to the main presentation. And T.Y., I'm looking forward to your talk. And yeah, please, let's begin.
Thank you. Yeah, again, thank you all very much for having me today. It's such a pleasure to be here. And before I get started, let me just give you a brief introduction about Netflix and myself. And you might have already know that Netflix started in 1997 as a DVD by mail company, and we only started doing streaming in 2007. Meanwhile, I was growing up in Taiwan, completely oblivious about what is Netflix. I only heard about Netflix when I came to the US in 2008 when I was attending Stanford for my PhD study. And I still can remember how exciting it was when I discovered Netflix as a service because there were some advertisement they posted in my dorm. So my study was on computer networks, and because I also love watching videos and TV shows, as a result, I tried to combine these two words into one and focus my study to help the networking researchers to understand how we can make the internet better in order to support applications like Netflix. So my study eventually led to some observations about the interaction between congestion control algorithms such as TCP and adaptive streaming algorithms, which I will talk more about today. And my observation eventually led me to an internship at Netflix, and I was so lucky to be able to do my thesis at Netflix. That just shows how open-minded Netflix was to a very naive student like I was back then. And then I stayed at Netflix afterwards. In 2019, I transitioned into the manager role and lead the streaming algorithm team here at Netflix. So what is my team is doing? So my team is streaming algorithm team. What does that mean? That means we design algorithms that help Netflix to adapt to the ever-changing network conditions. And we want to make sure Netflix playback always have great quality of experience. But quality of experience, that's such a big word. What does that mean exactly? That means we want to make sure when people play Netflix, everything works out smoothly. And we have hundreds of metrics to make sure that we can measure and monitor that smoothness. I won't be able to talk about all those metrics, but at a very high level, we want to make sure that the playback start right away with great quality and never stop unexpectedly. And that is easier to say than do, because we at Netflix, we provide service to a diverse array of networks and devices. Some people connect to us with very high-end connections such as 5G and LTE, but others connect to us with 3G networks and satellite. Yet others connect to us through a very different type of connection, cable or Wi-Fi. That's the network side. On the device side, we also have a lot of diversities. Some devices are super high-end, such as 4K and HDR, but others, we also have HD and SD devices in the mix. So our challenge is that how can we provide great experience for everyone that is in the service? And in order to do that, we have lots of work to do in every step of the way in our streaming pipeline. Starting from the production, we need to make sure we shoot in the highest possible quality of camera in that format. And then once we finish the production line, then we need to encode the video so that we can distribute them efficiently. Once we finish the encode, then we need to deploy them onto the internet, and more specifically to our content delivery networks. Once we have the files deployed, our job is not done yet. Once the customer click on that play button, we still need to continuously monitor the operating environment and adapt our video and audio qualities accordingly. I am an engineer, so I won't be able to talk more about the production side of things. So the rest of the talk, I will focus on the later three stages. The plan for the day is I will walk you through the 3 stages in our streaming pipeline and provide you an overview of our streaming system. Afterwards, I will also speak about how we use A/B test to fine-tune all the performance in this streaming pipeline and give a brief outlook into the future. All right, so let's dive in to the encoding part. Here, our goal is to make sure we can use the fewest number of bits to provide the highest possible quality. And we have gone a long way to do that. Before 2015, what we have done is to use one encode recipe for all content. And what we were able to achieve is using about 1,000 kilobit per second of the video encoding rate to achieve standard definition quality. But if you think about it, one encode recipe for all the titles, but all the titles have different characteristics, like the titles on the left, which is Aggretsuko and animation. Compare that to the other two, you can notice that the number of colors is fewer. There are more flat areas, and as a result, we could use fewer bits to represent Aggretsuko on the left compared to the other two. And that's exactly what we did. Starting from 2015, we start developing encoding recipes for each individual title based on their characteristics. And what we were able to do is to use a much fewer bits to achieve the same standard definition quality. Fast forward to today, we further extend that concept and start developing encoding recipes for each individual shot. And the reason for that is that even within the same title, such as Stranger Things, there will be some shot that is more action-packed, such as this bus flying over the sky on the left, versus there can be also some other shots that is more static and more conversational. And those shots, we could have used fewer bits to represent it. So once we did that, then we are able to achieve the same standard definition quality with a very low encoding bit rate, such as low as 250 kilobit per second. So I want to pause here for a second, just to think about what's the implication here. If we didn't invest in the encoding technology, we will need 4 times as much of bandwidth to support the same viewing hours. And that's the power of encode efficiency. And that's why Netflix invests so much into the encoding technology. And this efficiency also have other implications in terms of the data usage. In many parts of the world, the mobile plan still take account into how much data usage people have. And as a result, our customers are very conscious about their data usage. Before we did the optimization on the encode efficiency, 1 gigabyte of data can translate to about 1.5 hours of video watching. Fast forward to today, that number becomes 6.5 hours with our latest encode efficiency, which means about 7 episodes of Squid Games, and that's quite a bit. And our advancement of the encoding technology also means that we can achieve higher video quality with lower video rate. And historically, the industry has been using video rate as a way to indicate the level of video quality. But that's no longer to be true, because with the encode advancement, we are able to achieve higher quality with lower video rate. As a result, we start developing a new metrics called VMAF. And this is a measurement of human perceived video quality directly. So what exactly do we do to establish these new metrics? What we did is we conduct subjective tests to build a model of how encode artifact affect human perceived quality. We invite people to come into a lab, show them a bunch of video with different encode artifact, and measure and ask them to score the video so that we can build the model of that. Once we have the model, then we start applying the model to get VMAT score for every encode files in the catalog. And it is an open source project, so you can get our source code as well as the data set in the link below. And we're not done yet, of course. Right now, our focus is on 81. So 81 is a royalty-free encode, and it also provides a further improved compression efficiency. The last time I checked, we are able to achieve about 20% more efficiency compared to VP9. And what that means is we can achieve higher VMAF at the same bit rate. Right now, we provide 81 on Android devices, as well as for TV devices that have the hardware support, as well as PS4 Pro. You can read more about our current effort of 81 in our tech blog. All right, so that's the encoding part. Now that we have the file encoded, we need to deploy them onto the internet, and more specifically, our CDN. I know Alex has already provided an overview here, so I won't go into the detail here, but just to provide a very brief recap. Our guiding principle here is to deploy files to the places where to be as close as possible to our Netflix users. What does that mean is that because most of the users connect to the internet through their own internet service providers or ISPs. So whenever possible, when the ISP have the power and the space for us, then we want to embed our servers directly in their point of presence. When that is not an option, then we want to peer with these ISPs directly in the Internet Exchange Point, also known as IXP. And once we have done that, that means for users in Russia, for example, when they want to see Stranger Things, they don't need to go all the way to California where Netflix is to fetch the content. Instead, what we do is we proactively pre-position those content in servers in Russia, and users can go to the local servers and fetch those contents directly. It's a win-win solution for both Netflix and the ISPs, because for Netflix, that means users experience less congestion and less delay, and as a result, we can provide the best possible experience. For ISPs, they don't need to pay for the transmission of the file because we pay for the transmission and pre-position those files onto their devices. Cool. So now we have the files deployed onto our CDNs. Now it's a fun time. It's now the time for our customer to play video. And here our focus is to make sure we can adapt to the ever-changing network conditions. So what happens when a user clicks on play? What happens is that they will first go talk to our Netflix control plane, which sits on the AWS, the Amazon Web Services. Because we have lots of servers that is deployed onto the internet, we need to ask the control plane which server I should go to get the script. The control plane will look at which server actually have the content and which server can provide the best service, and reply to the client about which servers to go, and also which quality levels that we can provide on the server. Once we receive this list of servers and the quality levels, then the client will look at the local conditions and pick a rate that is that will optimize the experience to our customer. So let's say, for example, we believe that 8 megabit per second will be the best for the experience. We will go ahead, contact the server that we are supposed to go and fetch the content accordingly. So I mentioned to you that our goal here is to make sure we adapt to the network conditions. So why exactly is network conditions changes? That's mostly because the internet was kind of designed to not provide any quality guarantees or bandwidth guarantees. And there are also many reasons for the network condition to be changed. For example, it can be because people is on the move, or it can be because people are preparing some popcorns and using the microwave, and microwave is known to interfere with Wi-Fi. There are many, many reasons that network conditions can be changed. And the network, or the internet in general, is designed to adapt these kind of changing network conditions. And there are many different parts will kind of address this problem. For example, on the server side, we can use congestion control to adapt the server sending rate to the network conditions. I won't talk too much about it, but we also have a dedicated team that focus on this part of research. For my team, we focus on adaptive streaming algorithm and try to see how we can adapt the video and the audio rate to the changing network conditions. So that's the part we will focus on today. And so what's the trick? What's the mechanism behind the scene that allows us to adapt video quality according to the changing conditions? The key thing here is that we chunk up the whole video into small pieces. And we do that chunking for every quality level. I'm showing 3 here, but in reality, we provide 8 to 10 quality levels for each title. And the key thing here is that the chunking boundaries are all aligned across quality levels. And these alignments allow us to make individual decisions, quality decisions for each individual segment. So for example, in the beginning, the segment, in the beginning, we might think the quality, the conditions are great, and therefore we can select a high quality for the first segment. As the condition changes, if we sense the condition is worsened, then we will lower the quality to the lowest one. If the condition is improving, then we will step up the quality and eventually go back to the highest quality. The composition of all these decisions will be the resulting experience that our customer sees. So that's the mechanism. But we still need to design the algorithm to know which quality level we want to pick for each individual segment, right? So how do we design that algorithm? Just like all the algorithm design, we first need to know what is the goal of the algorithm. And the goal here is fairly simple. We want to make sure everyone have a good streaming experience. And we briefly talk about what that means. That means no interruption, or internally we say that's no rebuffers. We want to make sure the video is high quality. We want to ensure the playback starts quickly. And we also want to make sure the video quality is stable across the session. And there are many, many other metrics that we want to achieve. Achieving some of the goal is easy, but the hard part is actually achieving all of them. And that's because when you have limited amount of bandwidth, these metrics can be in tension with each other. For example, if I want to avoid rebuffer, I can always stream at the low speed rate. And I would only be able to get a rebuffer unless my network really cannot even support the lowest video bitrate. And those kind of rebuffers are really unavoidable, and there's nothing we can do. But if we do so, even though we can avoid rebuffers, we will suffer from low quality videos. On the other hand, if I really want to achieve high quality, then we can always string it at the highest possible bit rate. The problem is that if you don't have enough bandwidth to support such a quality, then you will suffer from a lot of interruption or rebuffers. And neither is great, right? So how do we design an algorithm that balance all these different needs to achieve a good streaming experience becomes the challenge of focus here. And so let's try to focus on these two first, and I will walk you through how we think about how to design an algorithm to achieve these two metrics: no interruption and high quality. So as I mentioned, that when bandwidth is something we don't know, we are essentially walking a tightrope. If we pick a quality that is much too high, higher than our bandwidth can support, then we will experience an interruption. On the other hand, if we pick a quality that is much too low, we will experience a low quality. So what is the conventional way? What is the most intuitive way to pick a video rate? And the most intuitive way to do so is, let's start from somewhere. We pick an initial video quality. We go ahead, download a chunk, and through that download, we measure the bandwidth and use that measurement to predict future bandwidth. And we select a video rate based on that prediction, download the next chunk, and do network measurement and rinse and repeat. That's an algorithm loop right there. So what's wrong with this one? This design, the problem is that future bandwidth is something we don't know, and it changes quite a bit. And as a result, to do an accurate estimation and prediction is super hard. Here is an actual Netflix session, and I'm showing you the bandwidth across time that we made, the bandwidth that we measured. So the y-axis here is the average throughput in kilobits per second that we measured over a chunk download. And the x-axis here is time in seconds. And you can see that for some chunks, we can measure a bandwidth as high as 17 megabit per second. For other chunks, we only measure about 500 kilobit per second. So the difference between these two measurements is huge. It's about 34 times of differences. And handling, because of these differences, handling the estimation is super hard, because at some point, we will estimate the capacity to be as high as 17 megabit per second, because we just measured the bandwidth to be 17 megabit per second, right? But in reality, it can be as low as 500 kilobit per second. So what that means is that if we pick a video rate based on our estimation, we will pick a video rate that is much too high, higher than the real capacity to be here. For example, it could be as low as 500 kilobit per second. And one way to remedy this is to always apply a safety margin, let's say S of t. But that means is that if we want to pick a rate based on the safety margin times the estimation, in this example that we just show you, in order for the rate we pick to be lower than the real capacity, we need to make this safety margin to be as small as 3%, or in other words, make a discount by 97%. That doesn't seem right either, because that works for that particular example. It might be too conservative or too aggressive for other example. So what can we do? The first thought we have is that if the bandwidth estimation is quite error-prone, we should take advantage of other signals if we can find them. So as a result, we come up with the idea of, hey, maybe buffer occupancy is another signal that we can use. And as a result, we start experimenting picking a video rate as a function of buffer occupancy. So why buffer occupancy? Because we believe that the true bandwidth is actually manifested in buffer occupancy. And in order to understand that, I need to tell you the relationship between bandwidth, the video rate or video quality that we pick, and the resulting buffer occupancy. So I'm going to use the rectangle in the middle to represent video playback buffer. And each slot in between is 1 video second. The pink rectangular you see here is a video chunk, and the height of it is represent the video rate. So the higher the rectangular, the higher video rate it is. And the black triangle here represents the buffer occupancy on the device. The output of this buffer is 1 video second per second, because that's how we normally play back the video. And the input of this buffer will be a function of the network capacity or the bandwidth, the real bandwidth, and the video rate. So if our video rate, the video rate we pick is actually higher than the capacity, what that means is that the output of the output rate of this buffer is higher than the input rate. And as a result, we will eventually run out of the video to play inside the play buffer and experience interruption. On the other hand, if we pick a video rate that is lower than the capacity, what happens is that we will pick a video rate that is much lower than what network can actually support. As a result, we quickly fill the playback buffer with very low video quality. Sure, we will not experience a rebuffer event, but our customer will also suffer from low quality video as a result. All right, so what I have shown you is that buffer occupancy is actually a state variable in the system. When the buffer occupancy is decreasing, that means that the network cannot sustain the video rate we pick. So what we should do is actually to decrease the video rate. On the other hand, if the buffer occupancy is increasing, that means we can actually support a higher video rate. So what we should do, we should increase the video rate. And as a result, that justifies how we can pick a video rate as a function of buffer occupancy. And that's what we did back in 2014. And afterwards, there are many research work to develop on top of it. But the buffer-based approach still doesn't solve many problems in this field. For example, there are many limitations. For example, for memory-limited devices, their playback buffer is super small, and as a result, we don't really have a lot of room for the buffer occupancy to tell us how the relationship is a relationship between the video rate and the actual bandwidth. There's no room for them to manifest that differences. And so given that limitation, the next thought we have is, can we improve network estimation and make it more useful? Buffer occupancy is still a useful signal as we manifested, as we demonstrated, but we want to incorporate other signals as much as possible. And also another limitation is that, as I mentioned, what we have trying to solve with the buffer-based approach is that we try to maximize the two QoE metrics, video rate and rebuffer rate. But there are many other QoE metrics that we want to optimize for, and buffer-based approach wasn't be able to tackle all of them at the same time. And so that's why there are so many other works after our initial work back in 2014, and they try to build on top of that to improve our understanding of the adaptive streaming algorithms. I won't go into each of them, but in summary, many of them work on improving the network prediction, and they apply statistical modeling and supervised learning to help us get a better prediction out of the available bandwidth. And also to address the issue of trying to optimize all quality of experience metrics at the same time, they try to formulate the problem into an optimization problem, and some of them build on top of the prediction work that I just mentioned and solve them as a control problem. Yet others will apply machine learning to solve these optimization problems, such as reinforcement learning and other machine learnings in the mix. I do want to mention the last pieces because this is super interesting. What it demonstrates is that they use was something allowed in the law in the United States, that is for universities or any nonprofit organizations, they can set up a TV relay station to provide a service as a nonprofit organization. So that's what they did, and replay a lot of TV stations here in the United States, and invite people to watch TVs on their website. Through the service, they are able to collect real life traces and evaluate all the algorithms that I mentioned before. What they found is that all these machine learning based algorithms, they really depend on the training data and the environment. But one thing we know about the internet is that it is a complex, diverse, and changing things as we continue to see. And as a result, all these learned algorithms suffer from estimation error and doesn't perform well on the internet, because there will be times that the operating environment is outside of the training data and outside of the training environment. So what they note is that only if we can train a model in situ based on the real data, that's the key for any machine learning based algorithm to perform the best. And what we do here at Netflix is pretty much similar to what they found. We try to make sure we optimize our algorithms based on the real operating environment. And as a result, we do a lot of A/B testing. So what exactly A/B test means? What it means is that let's assume we have two algorithms. One is the buffer-based algorithm, and the other is the throughput-based algorithm. What we would do if we want to evaluate these two algorithms, or if we want to fine-tune these two algorithms, what we would do is we will randomly allocate a number of Netflix members and randomly assign them to each of the treatment. And after some period of time, then we will collect the quality of experience for each individual sessions, and then compare the result across these two treatments. And we also have reporting infrastructure behind the scenes. After the test has been going on for a while, then we will generate a report, compare each metrics across the treatments, and compare the distribution across the treatments, and calculate the statistical significance so that we can understand the differences across the treatments. Even though we are very fortunate to have such an infrastructure and a user base to conduct the A/B test, there are still a lot of challenges that we are facing. For example, our current adaptive streaming algorithm takes in a lot of signals. We talk about the buffer occupancy, we talk about the network throughput, but because we also serve many different kinds of devices and many different kinds of encode, we need to take all of them into considerations in order for us to decide which bit rate to use. What that means is that we have a lot of parameters to be tuned and to be A/B tested. And as a result, it's a high dimensional search space, and there's no way for us to A/B test them all. So we need to be very systematic and methodological about how we conduct A/B test. So there's a technique that we use, which is the Bayesian optimization. And the way we utilize it is that we will conduct the first round of A/B test based on the engineering intuitions and the knowledge we have. And once we have done the first round of result, we will analyze the result and apply Bayesian optimization to find the next round of candidates. And then we do another round of A/B test and rinse and repeat. So let me go into the detail to tell you more about the technique we use, the Bayesian optimization. So what Bayesian optimization provides us is once we have a set of configuration values and the response from a QE matrix, let's say rebuffer rate, we will be able to have the observations from the A/B test for each configuration values that we are testing. And from that, then we can build a model between the configuration value and the buffer rate. And based on this model, then we can calculate what is the probability to minimize the rebuffer or optimize other QE metrics if that's a metric of interest. And based on that probability, then we will know what is the range that can help us optimize for these metrics, and that will be the candidate for the next iteration. Bayesian optimization can scale well. So instead of just optimizing for single metrics like a rebuffer rate I just showed, we can also try to optimize multiple metrics at the same time. And what that will give us is the Pareto. It's a Pareto frontier. You might be wondering, why is this a Pareto frontier as a curve, not a single point that will optimize for all of them? And that's because there are many trade-offs between the metrics that between each of the QE metrics. And we kind of touch upon the tension between the video quality and the rebuffer rate. But this kind of tension happens in other metrics as well. For example, if we want to have a low play delay, we can just download a little bit, but that means that we will suffer from higher rebuffer risk. On the other hand, if we want to lower the rebuffer risk, then that means we need to download a lot, which translates to higher play delay. So what we have from the Bayesian optimization is a Pareto frontier. That means on some of the point, it will lead to higher play delay, but in return, you will have low rebuffer rate. On other point, that means we will have lower play delay and higher rebuffer rate. But what Pareto frontier will give us is that given our operating environment, this is the best you can do. There will be some trade-off between the metrics, but this is what you can do the best. And then we can apply the context we know. For example, we know that on the mobile setting, people might tolerate higher rebuffer rate, but because people is on the go, they might want to have a lower play delay. Then we can set the operation point for the mobile setting for low play delay with higher rebuffer rate. And depends on different contexts, we might set different configurations for other devices or other contexts. And that's the power of Bayesian optimization. Depends on your operating environment. It can tell you where is the best curve that you can operate in, and then we can apply operational context to pick one that works the best for us. What works for Netflix might be different from what might work the best for you, but Bayesian optimization will give you the curve so that you can pick yourself. And there's still lots and lots of work remain to be done in every step of the way in our streaming pipeline. On the encoding front, as I mentioned, our focus right now is on AD1. We want to make sure we can roll out AD1 to an even broader member base. And on top of that, we are also actively working on 81 to support HDR as well. On the deployment side, because we want to pre-position our content in the most efficient way, we need to make sure we have the best possible prediction of the content popularity. And congestion control, as I mentioned, it's another way to adapt to the changing network conditions, and that's a very active research field at Netflix as well. On the streaming side, adaptive streaming algorithm, that's something we are still actively invested on, and we also invest in a lot of joint optimization. Perhaps the adaptive streaming algorithm needs to work together with the encoding design, or perhaps the adaptive streaming algorithm should work hand in hand with the congestion control algorithms. These are the things that we are actively invested in. With that, thank you so much for your attention, and I would be happy to take any questions you might have.
All right, T.Y., thanks a lot for the great presentation. I continue to be amazed that despite all of the years of improvements and optimizations with so many impressive results, there is still a lot of potential left to be addressed. And you've identified so many areas that there's still a lot of need in continuing research, continuing development, and hopefully bigger wins, bigger efficiency and quality wins ahead. I think we have about 10-15 minutes for questions, and I would encourage the audience to send questions via Telegram. I think we have a few questions already. We'll see if we have enough time to go through them. I think first is probably one a little bit more generic question. You mentioned that you came from the academia, and I know that you keep working like on the boundary between academia and the industry. Generally, what are the learnings and observations that you could share so far from your impressions of combining the research in like a very academic field with something that has enormous scale and impact that your team does at Netflix?
Sorry, I wasn't clear. What's the question?
So any learnings and observations that you've observed, like on things that are working well and they're effective, or things that could be better?
Got you. Yeah, I really enjoy how Netflix works for research. In many other companies, they have a dedicated research team, and they have to work with an engineering team to transfer the technology. But that's not the case here at Netflix. We believe only applied research team can work. And that means any researchers at Netflix, they also double as engineers, and they are responsible for the real system and its performance. And that model actually works super well, because only if you are operating the system, then you understand where is the real problem. But also because of our background in research, then we know what kind of technique can be applicable to the real system. So I think it's not really a learning, but it's an observation that this kind of model, having a research team that's actually also operating the system, can really work well.
Yeah, great. Thanks for sharing the perspective. And I know that you're not only a great example of someone who combines academic and applied knowledge, but also now is a very effective leader who kind of manages other researchers, applied researchers in the field.
I'm learning.
I know that you've talked about some A/B testing and improvements, but maybe you can share a couple of details on the most effective optimizations on the adaptive streaming side, if you can share any more specifics and any examples.
Yeah, I would say that it's less about individual tests that we learned. It's more about methodology. So for example, A/B test. How do you do A/B test for networking algorithm? Because there is an underlying assumption of A/B test, that is, treatments are independent from each other. But that is actually not true for a lot of networking algorithms. For example, if we have two sessions and one is more aggressive than the others, then that session can potentially grab available bandwidth from the other session. So when you conduct these two sessions in parallel, it won't be a fair comparison. And so how do you conduct A/B testing for this kind of algorithm that will actually share bandwidth or share any resource that underneath? And so my team actually spent a lot of time thinking through this kind of methodology. And the Bayesian optimization, for example, is another great example that constantly what we spend the most time on is not about learning which parameters works the best, because as I mentioned, the operating environment keep changing. What works the best today might not be the case for tomorrow. So what we need to do is really to have a methodology that can work well in this changing environment. And the Bayesian optimization is a great example. It leads us to be able to do adaptive experimentation in the most efficient way.
Yeah, I guess it's probably it's a good applied practice of the answer to many questions like, oh, what should I do? It depends on your problem domain. And I think you're just managing to optimize and making the learning of what it depends on very, very effective. And since you mentioned the Bayesian optimizations, can you share the details on like the typical life cycle? Like how quickly are you able to iterate on the test and kind of relearning the systems, like getting the results of one A/B test and feeding that into another cycle?
Yeah, right now, each cycle roughly the cadence we are doing each cycle is about a week, but that really actually depends on the metrics of interest and also how many people we allocate into the A/B test. For metrics that in general change very slightly, like rebuffer rate, and the reason for that is because Netflix has been optimized for rebuffer rate for years. And as a result, our rebuffer rate in most part of the world is very, very low. So the room for improvement is very low. And as a result, in order for us to observe any changes, we will need more time and more people. On the other hand, for other metrics like video quality, for example, video quality is something that is you can measure it for every single session. Compared to rebuffer may or may not happen. Most of the time, it doesn't happen. As a result, you need a lot of people to get a sample. But video quality, because you can get a sample for each individual sessions, and as a result, we might be able to get a read in a shorter time. So, there's no real answer per se, but worst case, it will be weekly. But if it's a metrics that is easier to measure, then we can do it in a few days.
Sounds good. Yeah, that's a really great perspective. Going to the encoding space, can you share the data on how many different encodes and different codecs that Netflix uses today? Because I think you mentioned BP9, you mentioned AB1. Like, are there any others that I used?
Yeah, we use quite a bit actually. We also support H.264. There are many others. It really depends on the device. Like on Android, we use VP9. On Chrome, we use VP9. But depends on the device support. We might use different encode on other devices. We do have a website that lists out all the encode we support. So I would actually encourage you to go to netflix.com there should be a support page detailed the encode we support.
Sounds good. Yeah, thanks for the pointer, T.Y. And then for the storing of the files, because you've mentioned about the adaptive streaming and that you rely on the chunks to make it work. Can you share any details on the storage of those files on the CDN? Is each individual chunk stored separately, or do you somehow like transcode the large file into the chunks on the fly? And are they stored in each encode separately, or do you transcode like in real time?
Oh no, we don't do transcode in real time. We pre-encode them into separate file, and so each file is for a different quality level for a particular encode. And we also separate audio and video because audio can also have different audio quality as well. And our adaptive streaming algorithm also work for to adapt audio quality.
And is it stored as a one large flat file, or are those files stored in chunks?
Yes, one flat file for each quality level for one encode.
And on the implementation side, then how do you make sure that the clients receive the chunks? Like what's on a lower level, what technique they use?
Right. So in the beginning of each file, we have some metadata to describe where the iframe start, and so depends on which chunk we are fetching. Then we know what is a byte range that we should request from that particular file.
I see. Yeah. Cool. Switching over to the trade-off between the buffer-based and the throughput-based algorithm, because you mentioned the buffer size as one of the kind of factors to see like whether the buffer-based approach can make it work. Are there any kind of more details? Because obviously there is a range of how big the buffer could be, and in a Netflix case, Netflix has the privilege of being able to work with the larger buffers. Like as the buffers get smaller, like what kind of warnings, what kind of recommendations that you can give?
Yeah, that's such a great question. Because there are devices have as low as 22 megabyte, and if you think about translating those to video seconds at a high end quality, that only translates to about 5-6 seconds. So for those devices, buffer level really doesn't mean anything. So because they probably can only store 1 or 2 chunk and that's it. There's buffer occupancy doesn't really give you that much of signal. And for those, we do have to rely on network measurements, and their tolerance for network errors is also much lower because the buffer size is just so low. There's no room for error indeed. So those are the most challenging devices. And honestly, for those devices, what we can do is to improve the encode in efficiency so that we can translate that same amount of buffer into more video seconds. And that's probably the most effective way to improve the quality in those devices.
And I think we have probably a time for one more question. Given the different devices, given the limitations on the devices, given different networks, do you think it makes sense to keep the single kind of engine, the single implementation of adaptive streaming across all of those? Or do you see the world where it just might make sense to have completely diverging implementations and code bases? And then how is it generally handled to Netflix?
Yeah, great question again. In some platforms, there's a reality that we do have to do different implementation. For example, Android, if we want to have the native support, you do have to have implemented in Java. Versus on other platforms, you do have different choices. And same thing for iOS. So as a result, we do have a number of implementations at Netflix. But our idea is that if possible, we want to use one general algorithms with different configurations. That's our principle, because that means we can share the learnings from one platform to another's with some tweak to adjust to the operating environment.
Okay. Te-Yuan, thanks a lot again for the presentation. Thanks a lot for the great Q&A session. For the audience, and we still have up to an hour more time. We are going to switch over to Zoom, and then we'll have a bit more interactive, more informal conversation. I would encourage the audience to join. And T.Y., thanks again for preparing and sharing the great talk.
Thank you for having me today.